Okay, so I hope you all can hear me. So let's get started with, so in the last few classes, we discussed various problems in probability and statistics. Probably first starting off with what is random variables and events and so on. And then we went on to joint distributions and conditional expectations. So we'll stop on probability there and use those concepts to learn a few things about reinforcement learning. We'll also try to see some implementations in Python, and then once we are fairly comfortable with the basic algorithms, we'll try to go into more advanced algorithms. Then I'll be introducing what are random processes like Markov chains and so on. And then we'll be dealing with more complex algorithms. That's the plan, sort of. But today we'll be starting with the basics. What I'll introduce the concepts of reinforcement learning slowly. In anybody has any question, please feel free to stop me. And people who are not yet in the Teams group, please join the Teams group because the materials are all uploaded there, the videos are there, and so on. Uh, okay, so let's get started. So what is so reinforcement learning? So before I start the theoretical understanding, let me give you a broad uh, idea of what reinforcement learning is. So basically, reinforcement learning is how living organisms are hypothesized to learn. So one of the major algorithms that living beings or life on Earth uses to learn, to survive, to evolve, and to reproduce is reinforcement learning. So reinforcement learning itself says that you interact with the world around you. That is, the first objective is interact with the world. The world gives you a reward. You learn actions that maximize your reward. So this is the very, very large goal of reinforcement learning. For example, so if the reward is to, if the goal objective is to be the most dominant species on the planet, a particular species, therefore all living organisms try to increase their population. So that's one of the reward signals that goes towards every uh, living organism on the earth, which helps them reproduce further and increase their population. Similarly for food and other things that tells your brain that you really like it. So that's the story. So I think that can get you excited because and learning reinforcement learning is like to trying to learn the mathematics behind how human beings or any other animals in this world function. So I like to, that's the motivation that can get you driven to learn RL. So, okay, so learning theory from a statistical point of view can be divided into supervised, unsupervised, and reinforcement learning. We have discussed supervised and unsupervised learning in the last course, which I covered entire GATE syllabus there. You can go with that and follow some of the machine learning and deep learning algorithms for supervised and unsupervised algorithms. A very, very broad another category of learning is called reinforcement learning in terms of learning theory. But I gave you the overview of reinforcement learning where you try to maximize your rewards. Now let us see a diagram to understand what reinforcement learning is trying to do. So the first concept of involvement in reinforcement learning paradigm is the involvement of someone called an agent. So the agent is who interacts with environment. as I was telling, or the world around it. So, there's an agent. The agent, so number one, the agent, they choose an action. So this box that I'm showing over here is the environment that the agent is interacting with. So they choose an action. The state of the environment changes. The state of the environment changes. And finally, the agent gets a reward. And this continues. Go to step 1. So this continues over and over iterations. So fine. So again, this diagram, if you look at it, so the agent is taking an action AN, and that currently the state of the environment is in SN. And then the third thing that happens is, since the action AN is taken, the environment changes its state to SN plus 1, and you end up getting a reward that is RN. So that's the set of things that happen in a reinforcement learning paradigm. And there is an end goal. End goal is maximize expected reward. So you try to maximize the amount of reward you get from the environment. That's the paradigm, large paradigm, set of paradigm that people work in when they're dealing with reinforcement learning. Okay. So let's take an intuitive example now. The intuitive example would be something like this. So say you are cycling. Okay. You're learning to cycle rather than cycling, trying to learn. So you rotate the handle of the cycle. This is an action. That is an action. So currently, say your cycle was balanced. So balanced. So this is the state of the environment. So say you rotated the handle now. Yeah, go ahead. And then it became, you lost your balance. So it's unbalanced now. Unbalanced, imbalanced, I guess. So that is the state that you are in. Now the cycle is so this is the cycle's balance or not being balanced is the state of the environment. So now say it became to the imbalanced state, so you get a negative reward because you see that you're going to fall and injure yourself. So you understand that this action that you took, that is rotating the handle, this action is a bad action. So similarly, you try to rotate the handle such that the cycle balances. So whenever you try to get a positive reward, so that the cycle goes forward. So this is how you keep on interacting with the environment and you end up learning the set of rules. So you never learn the Newtonian mechanics of the cycle going around directly. Instead, you learn through interaction with the environment of what small actions you need to really take to not fall. You don't write down all the Newtonian mechanics to solve the problem. That's the point. But you rather learn an implicit model for the world around you by using the rewards. So fine, I think this gives you a lot of, I think this is very clear for now. And you get an idea of how reinforcement learning works. If I'll give you a more concrete example, so and then you'll probably appreciate it more. So a popular example in this reinforcement learning, that's how the book I'll be using for most of it would be Sutton and Bartow. You can have a look at it. Sutton and Bartow, intro to ML, intro to RL. And there are examples like this lots in the book. So it says that, say To understand the building blocks of the RL algorithm, say you have a 3 computer systems, that is the source systems 1, 2, and 3. That is on the left-hand side of the screen, you can see. And there are 4 routers over here. So router 1 sends packets to router 2 or 3, and they in turn send it to the router 4, and then it delivers it to the destination. So the goal here is to send packets to the destination. And what do you desire over here? That is, you desire fast transmission of packets. And also you require no packets are lost due to buffer overflow. So these two are your goals. So you don't want your packets to be lost due to buffer overflow, or you don't want the packets to be waiting for a long time. So given these two goals, we are trying to now understand these various components of the RL algorithm. So what are the 4 components that we discussed just now? We discussed action, 3 rather. That is the action. We discussed reward at time t. So these are at time t, or let's write n for this. This is the reward. And you have the state Sn, which is the state. So now to describe this environment, first of all, tell me what are the actions that you can select. So here, do you agree that the only choice that you have is between P1 and P2? Only choice is between P1 and P2. So your action space can be either P1, choosing P1, or P2. This is very clear because everything else is fixed. Your action at a particular time could be either selecting P1 to transmit a packet or P2 to transmit a packet. The P being the path. Now, what is the state of the system? So say, now I define some numbers over here. Say Ni is the number of packets at the router I. So can you tell me what could be the state, what could be the state that describes this system completely? Any idea? So say this is the buffer that these packets have, and say this has 3 packets and this has 2 packets, and R1 has 1 packet in waiting. So can anyone tell me that what would be the state? What can we represent the state of the environment as? So do you agree we can represent the state of the environment as this tuple, that is N1 or N2 comma N3? Because you have no control over R1 and R4. All you can do is about P1 and P2. So I think N2 comma N3 describes the system very well, right? Because that's the only choice that you have choosing between the path 1 that sends it to router 2 versus the path 2 that sends it to router 3. Okay. Now, so if you understood this, the state is understandable. So for now, for this given example, what would be the state of the system at time n? Can you tell me? So there are 3 packets in router 2 and 2 packets in our router 3. So what is the state at this current time? What can I write this as?
3,2.
3,2. This is your state, current state. Very nice. So now my goal is to change this. So I have a new packet at R1. I want to send that packet to one of these routers. That's the action. I will either choose P1 and P2. So now, what are the 2 goals I want? I want fast transmission. So, and also I want the packets not to be lost. So at every end, so can anyone give me a reward function that does both of these? So at least one of them, say fast transmission. So that there are not a lot of packets waiting in the buffer. So some of the choices could be, do you agree? Minus N2, minus N3. So if there are a lot of high number of packets remaining in the at router 2 and router 3, you will be penalizing the agent more, right? Yes or no? So penalize the agent if lot of packets are waiting. Is it fine? So you are encouraging these routers to send off packets as soon as you receive them. And also you want no buffer overflow. So if you do not want buffer overflow, what can you do? So you want sort of something like this. So N2 to be same as N3. So another choice could be, a better choice could be N2 square minus N3 square, which inherently forces N2 to be close to N3, right? Because, for example, say you have 3 packets. The current state is 3, 2, and you want to send one packet to either. So you have, again, I'm drawing it over here, router 2 and router 3. Router 2 has 3 packets and router 3 has 2 packets, and you want to send it either through path 1 or path 2. So your loss function, your reward, whatever you are giving, would be maximum only when both are 3, 3, right? Instead of 4, 2. So if you have a sum of squares and they're constrained, each of them are constrained to be constrained to be equal to, the sum is constrained to be equal to k, the optimize received when all the variables are equal. So if I enforce this reward, I would, if there is an extra packet at R3 or at the source, I would send it to router 3. And then your new state, when you choose an action an equal to p2, will change to be 3, 3. Right? Any doubts? These are a few choices.
Please repeat this.
Yeah, sure. So what I'm trying to say is, say, what do I want? I want minimum waiting time. So minimum waiting time is, so I should get, if there are a lot of packets waiting in the buffer, the agent must be penalized. Yes or no? Correct?
Yes.
So currently there are N2 number of packets in router 2, N3 number of packets in router 3. So I say that at the current time, I will give you a reward of N2 minus N3. Okay. So this is one choice that I have. This is one of the lost choices. But what I'm also saying is, so there is a better choice than N2 and N3. So if I just have this packet can be either sent to N2 or N3, because the sum is same for minus 4 comma minus 2 is also 6, minus 6, and minus 3 comma minus 3 is also minus 6. Yes or no? Do you agree?
Yes.
But I am saying that I don't want to overburden one of the routers, because there's a chance that the buffers can overflow. So I'm saying if I put N2 square and N3 square, sorry, so then that turns out to be, which is better? 3 minus 3 square into 2 is 18. Or do you want to have minus 4 square minus 2 square, which is 20, minus 20? This is pretty trivial, right? So you would like to have minus 18, which is N2 equal to N3. That's what I was saying. So this forces the agent to send the packets not only to R3, but also R2 and R3 to send packets fast off to R4. Understood?
Yes. Thank you.
Any other questions? So this is just an example how you devise reward functions. So whatever you don't want, you give a negative reward for that. Whatever you want, you give a positive reward for that. So we define the state of the environment. We define some complete reward function for R2 and R3. Fine. So now,
Dada,
yeah.
It's like
Go
sort
ahead.
of intuition because you
Yeah,
were saying about N2 should be near about N3. So
yeah.
wouldn't it be better if it was N2 minus N3 whole square? Means the
So then
difference.
you would, it is right. But if it is N2 minus N3, there's a problem there. So you're suggesting what O3G is suggesting is it is N2 minus N3 is the reward function. But then you want to increase this reward. You can simply increase N2 very, very high, no? You don't want to make it small. You are trying to maximize rewards, right? The objective is to maximize rewards. Is it clear? So then
Yes, yes.
all the packets will be sent to, all packets will be sent to N2. Yeah, keep asking questions. This will be, it will clear a lot of doubts for a lot of people. So this is just trying to understand how loss functions work. Generally, they would be given by the environment itself, but sometimes we generally have to define the loss function or the reward signal to train a lot of reinforcement learning problems. Okay. So now let us try to understand some jargon in RL. So the first is how do you choose actions is the question. So for example, just now I chose an action of sending it to path one. So, but there should be a strategy, right? So I cannot just say that I have a list of actions. I don't have any other things in my hand. So how do I even go about choosing those actions? So say we choose actions based on something called as policy. A policy you can think of is a strategy. So this is a very, very important term in reinforcement learning. That is a policy. A policy is a map from state to action. It can either be deterministic or stochastic. We'll be seeing an example just now. So a policy is a strategy and it is a map from state to actions. So can you tell me who chooses the policy then? If it is a map between state to action, who chooses the policy? Who is having the policy? Who is taking the actions according to the policy? Therefore, the policies are for the agent, right? Do you agree? The agent chooses a policy. Say they choose a policy of selecting a random action. That is also a policy, right? At the end of the day. So something like that. So let us take an example. The agent chooses a policy, and that is a map between states and actions. So one example, since it can be both stochastic and deterministic, is this. So say the state is 1. Whenever you are in state 1, you take an action A. Whenever you are in state 2, you take an action A. So currently the states are 1, 2, and 3. Actions are A and B. Right? So you can put a table over here, and then you can write down the actions. So the first is an example of a deterministic policy or a deterministic choice. The overall here is a stochastic policy nonetheless, because 2 is stochastic. So where 2, whenever the person is in state 2, they choose either between action A or B, with probability 0.7 and 0.3. So now you tell me, so pi itself can be defined as a conditional probability is what I'm trying to say. So pi A given S is a probability function. For discrete case, it can be a PMF, for example, in this case. So tell me what would be the probability. This is what we were defining yesterday. That is, it's a conditional distribution. So okay, so what is given state 1? What is the probability of selecting an action A? Can you tell me, anyone, for this table? So given state 1, so this is nothing but a action A is equal to, so instead of P, I'm writing pi. That's because that's a convention in the field. State is equal to 1. So what is this probability? Pi of A given action A, given the state you are in is state 1. Yeah, Utrish, tell me.
One only.
Yes, because you can only take action A, right? There's no other, it can't take any other action according to the agent. Now, similarly, pi B given to someone else. 0.3 is given to be that. Yes. Similarly, pi A given 3 is 0. Because you are only choosing B here, so it's 1 minus probability of B given 3, which is equal to 1 minus 1, that is 0. Fine. So this is what you define as a policy. So a policy, we'll see how we learn policies, but the idea is it's a mapping from the states to a set of actions. Right. So now, next, so how we have seen what is a policy, and now we try to evaluate our performance. So what do you mean by when you are performing good or not? If you are performing good, you get a high reward. So just let us write it down. So good performance is analogous to high reward from the environment. Yes or no? And bad performance is, so please get the intuitions clear. Once we get into a lot of maths, these intuitions must be there in the back of your brain. Otherwise, the maths would become very, very monotonous. Low reward from the environment. So whenever you are performing bad, you try to change your actions. For example, you go to a restaurant and you get a bad food, that's a bad reward for you, so you never go back to that restaurant again. The action being currently going to that restaurant, and the state meaning how you like the restaurant currently. Something like that. You just keep making up examples like this, you will see that RL is all around you. So, okay. So how do you evaluate your performance based on rewards? So we define something called as the reward function for it. So reward signal helps in defining the goal of the RL problem. For example, I'll be calling it reward function or signal. So in neuroscience, they call it signal. In electronics, they call it signal. In computer science, they call it a function. Anyways, so a reward function would tell you if an action is good or not. So let's just take an example. So reward function, so here it should be R, sorry. So reward function R is a mapping from a Cartesian set or product of state and action to a real number, is what I'm trying to say. So what does it mean? Or a set of rewards also. So this could be a set of rewards, real numbers or set of rewards, set of rewards. It could be discrete, continuous real numbers, anything you want. So what do I mean by it? So if given a state and an action, this should return a reward. So SN, AN, this should return RN, is what I'm trying to say. Right? Again, your reward function can be both probabilistic as well as deterministic. So let's take an example over here. So I think my, yeah, it's there now. So now say the same example I'm giving you. Say you have a state, you are in state 1 and you take an action A. So it says that whenever you take an action A, give me a moment. Yeah. So these two, the first two, you can see the first two rewards over here. Yeah, you take an action A. So that can give you reward 1 or reward 2 with probability 0.6 and 0.4 respectively for this reward. Okay, so now, so this can be a deterministic deterministic function or a stochastic probability distribution itself. So what is the probability that a reward is equal to R1 given state is equal to 1 and action is equal to A? So this is also known as the reward signal or the reward probability, the reward distribution. So tell me, what is the probability that you're going to get a reward R1 given the state is 1 and action is equal to A? It's given to you that these two are occurring. What is the probability that you will get a reward R1? Anyone?
0.6.
Yeah, it's mentioned over here. It's 0.6. Okay, let's take another example. Probability of reward equal to R3 given state is equal to 2 and action is equal to, say, B. Can you tell me? Action is B and state is given to be 2. So you see state 2, action is B, always chooses reward 2. So it is 0 because you're never going to get a reward 3 when you are in state 2. So we'll be so this is just an example to keep you familiarized with conditional distributions as we did last time. But yeah, feel free to stop me if you are not understanding. Similarly, probability of reward is equal to R2 given state is equal to 3 and action is equal to B. Would be, so state 3, action is B, and you choose a reward. And you are, what is the probability of choosing a reward 2? This is 0.2. Is it clear to everybody? So what I'm trying to point out to you is that every time you go to a place, for example, you take an action, even if you take the same action and the environment is in the same state, the reward could be still stochastic, right? So it is not going to always be following the a discrete or a deterministic case as we see in this state 2 and action A. So for example, you go to a biryani shop and you order biryani. One day you could be very happy with the biryani, and the same shop at the same time of the week could give you a very bad biryani the next time. So that's what I'm trying to say. The reward could be changing over time as well. So we account for all of these over reward functions. That's what I'm trying to convey to you. So we understood what is a policy, what is a reward function, which can both be deterministic and stochastic. We'll see some examples. We'll start with smaller examples and then go to more difficult examples. So what ends up happening is when you are in state 1, you take an action A, you get a reward. You go to state 2, you take action R2. You take an action R2, you get a reward back R3, and you go to S3 and so on until it terminates. So this is the it keeps on, the sequence of events goes on in this process. The process goes on in this form. So what's the process and all will come to in due course. Don't worry about it. Okay. So what is the last thing is, how do you evaluate? How do you choose a policy, or how do you take actions is the question. How do you take actions? So until now we understood what is a reward, what is a policy based on which you take actions. But I'm asking you now, how do you, I understand that you are going to take you will have a policy and so on, but you will always not have a table that will tell you, I will take this with this probability. You will have to quantify that this action is this much, this beneficial. So that is given by what is called as a value function. So value function V pi of a state is a mapping from the state to a reward, to a real number line. So it can be a reward, anything. So it's a real number. So what does it mean? So it means that given that you are in state S, what is the expected reward you're going to get? So the value function is defined something like this. So I equal to 0 to infinity. Gamma, we'll come to what is all this, but for later in a later class, but sometimes defined this way. So what does it mean? Will come, gamma is less than 1. This is called discounted reward. But the idea is, if you ignore gamma for the time being, it is like R1 plus R2 dot 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 R infinity. It's the expected reward given that you start from a state S, right? So that's called a value function. So and it actually helps you take decisions. So you may not really see that it is helping you take decisions, but if you see the Q value function, it will immediately help you understand that. So this is for a particular state, but Q value function for a particular policy is again the sum of rewards the expected sum of rewards given state is equal to S0 is equal to S and A0 is equal to this is your A, right? So this is what is defined as. So being in state 0, you are in state 0 and take an action A. So that what is the expected reward you're going to get in the entire trajectory is called the Q value function. But it doesn't, we'll come to it. But what I'm trying to convey over here is this actually helps you selecting an action. How does it help you? Do you agree the best action at a particular time, A star, is argmax of A, QS, comma A? Yes or no? So given a state, the best action you can choose, because since pi is a mapping from your state to an action, do you agree that it is the best action that you can choose is the one that gives you maximum expected reward? Yes or no? This is what I'm trying to convey. So this helps you take decisions. Is it fine with everybody? Any questions?
Please repeat this.
Okay, so let us take this example. Say you have Q of S comma A, right? What is Q of S comma A? Let us not go into the math. First, let us understand the what does it signify? It tells you, given a policy that you choose, what is the expected reward. So what is, say you choose to study, what is the expected reward throughout your life? What would you get from a career and so on, versus taking another action, whether in sport and so on. So and accordingly, you choose the best action. So you may think that a particular action is going to give you more rewards, and that action is being chosen. That's what I'm trying to say, right? And we'll also see that this also helps you learn the policy itself, but we'll come to it. So do you see if the policy was perfect, you could select the action if pi is optimal. Do you agree the best action is the one that maximizes the reward? Yes or no? For an X, the best action. Shayon?
Yes, yes.
So because it is defined that way, so every the function is a, so for every state, so S1, S2 dot 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 Sn, and every action, you will have a number. Say, so let us define the number ij, number nij, and so on. So in this matrix, say that you are in a state I, you will select whatever is the maximum in the column, right? You'll select that action because that's the best action you can choose to get the maximum reward. Do you agree?
Yes.
So that's what I'm trying to say. Rij. So this is the Q matrix, Q S comma A matrix. Okay. I think that's the foundation. So this is all that what you'll be expecting to see in the course, but yeah, it's just to give you a primer of Q and so on. So, but now it comes a very, very philosophical question. So you do not know what the reward is in store for a particular action. So how do you? So the question is, you don't know what reward is in store for an action or state action pair. Right. So what do you do? How do you estimate it? Any idea? So algorithms or human beings, what do they do? Or any animal? So you would see, for example, I would give you a real example is going to come up, but anyways. So I'll give you an example. Ki there are restaurants, RST1, RST2, and RSTN. Right? There are N restaurants that you have. So now you have never been to any of the restaurants. So what would I'm trying? So all I'm trying to tell you is, say you are in a new city now, and you do not know any of the restaurants, and there's no Zomato, and you can't really trust Zomato and Swiggy. So what would you do? So to understand if the restaurant is good or not, just give me an answer. This is very simple. So you want to go out on a yeah.
I
So you
will
need not
check. I
you
will check.
yeah. You'll go to a restaurant. Say I choose restaurant 2. I'll go to restaurant 2. Go to restaurant 2. Just give me a moment. Okay, sorry. So I'll go to restaurant 2 and I will evaluate how good it is. Say I give it a rating, say 3 out of 5 or something. And then the next day, I go to restaurant 3 and give it a rating, say R3, RST3. I give it a rating 4 out of 5 or something like that. And then every time, say I again go to restaurant 2 and I take this time the food was better, so I give it 4 out of 5. So I take an average and now it becomes 3.5 out of 5. So now this is continuing over a long time. So so this is the idea of exploring. So exploring a lot of things around you. So you go to each restaurant, you're exploring them. And then when the time comes, you think that you're very confident of your decisions, of your experiences in this world. You start to exploit. Since you know, say the restaurant 3 is always very good. So you always keep on going to the safe restaurant. So that's what is called an exploitation. So there are two things over here. First is explore to estimate the rewards. Estimate the reward function or the value function, whatever you want to estimate. Secondly, choose actions that maximize the rewards. Fine. Choose actions that maximize your expected rewards. Not rewards, but expected rewards. That's the idea. But there is a dilemma over here, right? So whenever you're exploring, you're not guaranteed success. But so what is the problem with exploration? What is the merit and what is the demerit? Merit is you get better estimate for an action. And a demerit is, can you tell me what is the demerit?
A
Anyone?
lot of chances are taken and may not.
Correct.
I may not get good rewards in each. So
Very good. There is no chance, there is no guarantee of success. There is no guarantee of success. You can get a bad reward. That's why people keep on saying you learn through experience. Why do you say you learn through experience? Because you estimate the value function. So this is very philosophical, but RL is like, it's good to have this philosophical idea when you're studying RL, because with experience you may get bad rewards, you may have bad experience, but at the end of the day you are wiser. That's the idea, because you have a better estimate for the world around you. And again, exploitation, merit is more chance for success. Success, as you are likely to exploit only when you are confident. Now, what is the demerit? What is the demerit of exploitation? Can you tell me? I'm waiting. The demerit is if you go for early exploitation, if you go for early exploitation, comma, you would not know the world around you. If you do not take enough chances, you would not have an estimate of how the world is around you. So for example, if I go to restaurant 3, restaurant 2, for example, and I have an estimate, because now all the restaurants have an estimate of 0, I have an estimate of restaurant 2 to be 3.5, which is decent. And I say that, no, I am very afraid. I will not go to the rest of the restaurants. They will give me a bad food. So let me go to restaurant 2. It's decent. I will keep going there. So that a restaurant may be out there which serves the best food all the time. So you may not ever reach that restaurant again. So that's the dilemma of exploration versus exploitation. So you need to know. So this is also a very, very, um, very intuitive hand wavy thumb rule based approach, where you need to know where to stop exploring and start exploiting. Okay, so if you do not have any questions, I will request you to, I'll go to the next part, but yeah, I'll wait for a moment. But any questions? So these are all the founding blocks. So we'll be now doing an example, more concrete example of states and actions. And then we'll be going to the first RL algorithm called the Bandits. But yeah, any questions? Okay, I hope this is clear. So now, so say we have to play this simple game of tic-tac-toe. And you want to train an RL agent to play it. We may be doing it in the later in the course, but for the timing, let's try to find out the building blocks of this game. So say the player 1 plays X and player 2 plays 0. So first you are asked to define a state of the current environment. So say player 1 is of importance to us. Player 1 is of importance, or whatever, I don't know, importance currently. And they play first is my is what I'm trying to say. So say you are trying to learn a computer game, so where the human would be playing and you are training a agent to play against it. So say player 1 is the agent. So now I tell you, define a state for all of these, for this tic-tac-toe game. So first tell me, at a particular time n, at a time n, for the square I, how many possibilities are there for square I? How many different things can square I hold? Anyone? What can square I contain? Is what I'm trying to say. Every square, for example, this cross, 0 or empty. Do you agree?
Yes.
Good. It can be either of these three at state I. So at I. Okay, so we can let us define a state in this form. The state being Sn being S1, S2. I can put some superscripts to denote n. Sn, S9, and I will also define an S10. Can you tell me why do I need to define S10? Can you tell me? S10 will tell me who played first. That is cross or 0, right? If cross played first, so you can really able to find out who's. So this will tell you whose move is it next. Whose move is it next? This is a design choice that I have. So to tell how many who has played the game, who started the game. So say for example, in this example, the blue ones, the X started the game. Say without loss of generality, cross started. And this white is yet not there. At N, it is empty. So can you tell me what is the current state of the environment? So I define the state. It is. So first of all, tell me how many states are there? The number of states for this game. So tic-tac-toe only has a finite number of states. Tell me how many states are there. So what is a state here? So every element in the state vector can be, how many options are there to fill the state vector? For every element in the state? 3. So 3, 3, so on, 3, and the last one is 2, right? So number of states present in this game, how many states?
2 into 3 to the power 9.
2 into 3 to the power 9. People who are thinking, how did it come about? So it's like 3 into 3 into 3, 9 times, because that's the number of possible combinations I can have, into 2, because that's the number of combination for who plays first. Very good. This is around 39,000 states only. So chess and all, they all have finite number of states. Yeah, so most algorithms end up training RL algorithms for training chess and so on. So this is pretty small state space, but let us now try to understand the current state. Okay. So the current state Sn, same, which is currently S3 would be, can you tell me? Because there are three play moves have been played till now. So what is the current state? If I have to write down the current state, someone? S1, S2, S3, S4, S5, S6, S7, S8, S9, and S10. Tell me each of the values. Anyone? So currently at box 1, what do you have? You have a cross. So I put a cross. And at 10 also I put a cross because the first player was y, X. So now what will be state 2?
0.
No, state 2 is yet to come. At step n, it is empty. So let us just erase this for the time being. Yeah, it is empty, right? So it's E. 3 is X, 4 is empty, 5 is 0, 6 is empty, 7 is empty, 8 is empty, 9 is empty. Okay, this is fine. Clear to everybody? So now, say I take an action. The action at n is to change an E to a X or 0, right?
State 2.
Is to change. Yeah.
Please
So now
explain state 2.
which one do you want? Yeah, tell me once again.
Please explain state 2.
State 2 is currently empty is what I'm trying to say. So it's the game started like this, that cross, then you played this circle and then this person played cross, right? And now state 2, I am playing. Now I take an action. The action is the state 2 changing into 0 is what I'm trying to say. Is that clear? It was just marked star because, yeah. So the new state S4 is this X0, X, E0, E, and X. So this is your new state, that is state 4. So now you keep continuing till a player wins. That's the idea. So the action is understandable. The state is understandable. What is left? The reward. So what do you think should be the reward? Tell me. If I win, what should be the reward? If I lose, what should be the reward? If there is a draw, what should be the reward? And every state, what should be the reward? Say this is reward 4, what should it be? It should be 0 because you are not won or lost, right? 0 intermediate reward. Say +1 for winning, -1 for losing. So you'll see that the algorithm automatically learns to win. The best strategy, 0 for draw. Right? If I train an algorithm, which will come to how we do that, but if we train an algorithm, if that algorithm exists, it will always try to like winning. Yes or no? So do you like the reward function? This is Rn. Okay. Any question?
Is this the final reward? +1 after
I
3
think we lost your
cross
connection
or
at 3.
1.
Is this
the final reward? Means if 3 cross
yes.
come in a line.
Yes, that's what I'm saying. So for example, say you are the circle player and say you had 1 and you won. So if you had 1 and then you would get a reward of +1. But if the crosses came in a line, you would get a reward of -1. That's what I'm trying to say. So if 0 is of importance. Fine. So I think it's
What is
player
an
2 is of,
intermediate reward?
yeah, I'm going to it. So do you agree that we had formulated, do you remember this graph? This graph. So whenever an agent is taking a action, the state is changing, yes or no? We are seeing that whenever you took an action, put a 0, it went to state n+1, yes or no? Who was this? Can you please?
Yes.
Okay. So Rudev, you asked the question or someone else?
Yes, I did.
Okay. So what I'm trying to say here is, so every time, say for example, so when you played this 0 in between 2 and 1 and 3, right? The game has not stopped yet. Has it stopped yet?
No.
Okay. So now say you are in state 3, you take an action A3, which was converting S2 3 to 0. So game has not stopped. The environment will give you some reward, right? Because you have the environment will return a reward R3 of 0. Okay. And you go to state 4. Fine. And it keeps on happening till you reach the terminal state, which is either a draw or a win or a loss. Yes or no?
Okay, okay. Got it.
In between, you will get all rewards to be 0. And only at the end, you will get a -1 +1. And that will be propagated backwards for the agent to learn. So that is the only signal the agents will know. So when you learn strategy to play this game, tic-tac-toe, you must have learned in this way. So this, if I put across here, I will never win. Things like that. So the algorithm is very similar to that as well. So if we get time, we'll be writing the code for this algorithm. I think will be a fun exercise to see the algorithm learn itself to play the game of tic-tac-toe. Okay, so I think this gives you a broad idea of what reinforcement learning is, and what are states, what are actions, and what are rewards, what are value functions, and what are reward functions. But now this is all in the air and it's very vague that I've been talking about the past hour. It has been very hand wavy and so on. It's not been very rigorous mathematically. So let's try to find out the first reinforcement learning algorithm where there is only one state, always one state, and only actions determine your reward. That is something like the restaurant case that I was explaining. Right? It's easy to explain and it's also easy to get started. And you will always, I think this will stay with you for the rest of your life because it's a very nice algorithm and it gives you an entire understanding of how RL works. So multi-armed bandits is a game that people play in casino. So this is the bandits means dacoits. And in casinos, they have this weird named game called bandits where you're trying to pull the levers and you'll get some reward for it every time you put a coin into the casino game. So it's like you have K arms for the casino thing and you just keep pulling it and you try to see which gives you the best reward, say some soft toys or something. And you're trying to estimate which is the best arm that you can have. Okay, is the problem's definition clear? So there are K actions that you can choose from. Only one action, only one is good. The rest are not good. I mean, you want to choose, the idea is one state is there, you want to choose the best action. You want to choose the best action is the question. So what do we do? We'll have to try to figure out a strategy to do that. Okay. So objective is to estimate the value of an action and using the estimate of the value of the action, take up decisions. So it's like first explore which arm is good to then exploit that arm. Okay. So they say there are K actions that you can choose from. Here we will estimate what is the value of each of the action. So that is very simple. The reward function doesn't change, anything does not change. So this is called a value action function or an action value function. What is an action value function? Action value function is, say, a function Q. Say this is the optimal action value function, which is the mapping from the action to the rewards. So do you remember the value function was a mapping from a Q value function was a mapping from the state and action to the reward, which I was telling. Since there is only one state which is fixed, it's a mapping from just action to reward. Is this clear to everybody? Right? So as I was saying, Q of A is defined as the expected reward given that you choose an action AI or an action A. Okay, this is the expected reward, is what you define this as. Fine. So, okay, very good. So you, if I say that, okay, what is the on pulling this arm, what is the expected amount of reward I will be getting? Very good. So now, people who did my class last day, do you agree this is a random variable? Yes or no?
Yes.
It is a random variable. It's a function of AI. So it's a random variable of a in terms of a function of the action. So if I fix it to be this, then it is a constant. But if I don't fix it and I put 80, it's a random variable over the action space. So depending on the action, you will get a Q value function. So this is conditional expectation again. But we're not going to go into all the details again of conditional expectation, but let us take, for example, Q star of a particular action. So RT given AT equal to A. What can I write this as? Please don't see the left. I think we have already done that last time. So say all the rewards that you can get. So say the rewards RT that you get from selecting an action A is given by this. Say RT is the random variable, so you can get reward R1, R2, Rn. And the probabilities are P1, P2, and Pn. So what is the expected reward you will get? You'll get RT, probability of R, the reward at time being R given AT equal to A. Yes or no? The conditional, this is the definition of the conditional expectation. Yes or no? We defined this last time. The reward into the probability of getting that reward, right? The sum over that. Right? Any questions? So this is just the simplest probability function. We'll be going into more complicated probability functions. So any questions, you just ask here in here itself. Okay. So the idea is this is not known to us. Right? But is it the end of day for us if it is not known? Is the question I'm asking. Is it the end of day? Can I estimate it just by observing the world around us? So this is not known, is what we discussed. The probability function P of RT given R given A is not known. The distribution is not known to us. So how do we devise an algorithm to do it? Do you remember the weak law of large numbers? We did it in the first class. What did it say? Say the expected value, say you have a random variable S, which is 1 by n, 1 to n, xi, right? Where expected value of xi is equal to mu, the variance of xi is equal to sigma squared. Okay, and xi's are IID. So what is the expected value of the, say, let this write as the empirical average. Empirical average. What is the expected value of x bar? Can you tell me? By linearity of expectation. I'm doing it again. Which is equal to n mu by n, which is mu, right? Which is also equal to the expected value of xi. Yes or no? Similarly, what is the variance of x bar? We did it for independent events. Variance of 1 by n summation of I equal to 1 to n. I think some of you solved it also. Is 1 by n squared, sum of the variances xi, which is equal to n sigma squared by n squared. So this, whenever there's a scalar, you take it out of variance, it becomes squared. We have done that as well. So sigma squared by n. So as n goes to infinity, what happens to the variance of x bar? It
goes to
becomes
zero.
0. So very good. So what does it mean? So this is weak law of large numbers because only we are seeing the second moment, but that's all that I can give you now because it's strong laws are very difficult to prove for this class. So the idea is there's no variance left. So it's just a spike, a delta function at expected value of xi. So what does it mean? So if you have enough samples, if you just take the empirical average converges to the actual expectation. Yes or no, everyone? Any questions? So this is the idea behind any Monte Carlo estimation. So this is whenever you are doing an algorithm in reinforcement learning, in machine learning, you won't have actual expectations, but you will have data from the distribution. So what you will be doing is, can you tell me what will you be doing? So if, say, instead of Q star of A being expected value of R t given AT equal to A, what can I, let us define an empirical, this is the Monte Carlo sample. Let us define a Monte Carlo sample Q. Okay. At a particular time t of A to B. How can I define this? Can you tell me? Let's write n for simplicity. At a particular n is the at time n. So time means at n equal to 1, choose an arm, 2 again choose an arm, and so on. At n, what would be the Monte Carlo sample? What would be the empirical average? Can you tell me? So again, see, for the expectation, I just took the average of the outputs of the random variables. So it's like, what is the reward you got when you chose the arm A, right? So do you agree this is the rewards Ri I equal to 1 to n, indicator of AI is equal to A by number of times I equal to 1 to n, indicator of AI is equal to A. Yes or no? So out of this n times, say you selected 5 or 10 times, action A was selected 10 times. So indicator function is 1 if AI is equal to A, 0 otherwise. So what is the denominator going to tell me? It's going to tell me a number of times A was visited, right? Up to time n. Do you agree?
Yes.
This is and this is going to tell me, and the numerator will be Ri whenever action AI was equal to A. Yes or no? Fine with everybody?
Yes.
So the Q value function. So if I only choose an action A, if I only choose an action A can be written as summation of I equal to 1 to n, 1 by n, capital N, let me write, Ri. Yes or no? Do you agree? If I only choose action A all the time, is what I'm trying to say. Fine with all of you? Because all of these will become 1 and the new denominator will become n. Fine. So now we have got the estimate for the Monte Carlo sampling at time t. So I think I wrote that's fine only. NT is fine. So now I am told to derive an algorithm to update this online. So given Qn of A, say I choose an action A, again, what will be Qn plus 1 of A. Anyone? How will I do this? Let's first write down Qn plus 1A. If only A's were selected. Tell me, what will it be? Is the summation of I equal to n plus 1, 1 by n plus 1, yes or no? I'm waiting. Is everyone following me?
Yes.
So this is just the empirical average. This is when only action A is selected. Okay, so now can I multiply and divide by n? Summation of I equal to 1 to n plus 1 Ri. This can be written as, I can break this summation into two parts, 1 to n Ri plus Rn. Can I write it this way? This can be further written as 1 by
This
n.
should be Rn plus 1.
Which one will be I? Hello.
Should be Rn plus 1.
This n plus 1, correct. Thank you. That will be Rn plus 1. Perfect. Sorry. So I to n Rn by n plus 1 plus 1 by n plus 1 into Rn plus 1. Agreed? Can I write this way? Fine with everybody?
Yes. Yes.
Okay. So this thing is, what is this thing? This is the
Qn.
Qn of A. Very good. Qn into n by n plus 1 plus 1 by n plus 1 Rn plus 1. Fine. Say now I add 1 and subtract 1 from the numerator here. So what do I get? I get Qn of A minus or plus 1 by n plus 1 Rn plus 1 minus Qn of A. Yes or no? This is just exponential averaging. This is fine to everybody. So this is the expected. This is called the error. Expect the error. This is called the error in the reward. Error in reward expectation. Okay, so whatever, say you expected a reward of Qn, but you got instead a reward of Rn plus 1. Got, and this is expected. So the difference tells you, so what is the error in your expectation? And that's what is used to update your estimate of Qn to Qn plus 1. Okay. So as n tends to infinity, Qn tends to Q star. We'll see why this is next time using an ODE case. But for today, we'll be considering that is the case. So a general equation would be Qn plus 1 of A is equal to Qn of A plus alpha n Rn plus 1 minus Qn, where this is the learning rate or step size. So 1 by n plus 1 is a valid step size. We'll also check what are the valid step sizes. So alpha n is 1 by n plus 1 is a valid step size. So we'll also choose other step sizes and see, but for today, we're not going to do that because that will require some foundations. Okay, so this is the learning rate or step size, and you have this is the error signal. And this is the update. This is the update equation. Fine. Great. So now I have Qn plus 1 is equal to Qn plus alpha into Rn plus 1 minus Qn for all actions. Fine. Now I'm asking you. So now since you have selected a Q function, so it tells you, so what is Q again? Q is, if you recall, is the expected reward for an action A on selecting. Okay, we expect a reward for an action A. So now if I'm told to exploit this strategy, what will you do? How will you choose the action? Choosing an action now. How do you choose an action? At AN. Because to learn the algorithm, we will have to choose an action, right? How will you choose the action? Anyone?
Sir, the one with the highest Q
Very
n
good.
of n.
Yes. So this is called the greedy action selection. So now, can anyone tell me what is the problem with the greedy action selection? So you initialize all the Qns to be 0. So now you select an action based on, you take a random event and choose estimate it. It becomes positive. So now you'll keep on choosing that action, yes or no? So this only does exploitation, but no exploration. Is this fine with everybody?
Yes.
So an alternate action selection is called the epsilon-greedy action selection, where you are greedy, 1 with probability equal to 1 minus epsilon, and random with p equal to epsilon. So every time you are random, you are exploring. Every time you are greedy, you are exploiting. Fine. So now tell me, write it down. So your action AN will be, if this is epsilon greedy, with probability 1 minus epsilon, argmax of A, Q of A. Fine. Sure. I think this is n plus 1. As we are defining, I think in the, let me just check how we defined n. Yeah. No, okay. This is n only. For a state, for a current action, we just select an. And with epsilon probability, uniform A1, A2, dot, 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 AK. Is it fine to everyone? So uniformly select, that is AI is selected with probability 1 by k. Is it okay? So every time you can either toss a coin with epsilon probability you will be exploring, with 1 minus epsilon probability you will be exploiting. So this is exploiting and this is exploring. So now let us write down the algorithm and then we'll see the Python implementation. The algorithm, can you tell me, first step is to repeat?
Initializing.
Okay, initialize Q to all zeros. Then what do I do? Say I define a epsilon greedy action selection. Action selection. I call this. This will give me an action AN. Yes or no? This will give me an action AN. Okay. Now, based on this action, I sample a reward from the environment with an action. This will give you Rn. Once you get Rn, or rather Rn plus 1, sorry. And then once you get Rn plus 1, what can you do? Qn plus 1 can be updated as Qn plus 1 by n plus 1, Rn plus 1 minus Qn for all, of course, for the action An. Yes or no? Repeat until convergence.
But sir, this n
Yeah.
will be then different for all actions A, right?
Yes, correct. So this will depend on this. This is as we had defined. Again, going back is this, right? This n would be nt of A. Sorry, you are right. Nt of A. So this will also update nt of A plus equal to 1. So who told me? Please don't call me sir again.
Oh, sorry, I'm sure of it.
So Rudeep, yes. So nt plus 1 would be updated every time number of times you visit it. So because we are finding it for a particular area. Is it clear to everybody? Whatever it is, n of an is the number of time you visit it. Right? So if you visit an, you update the number of times you visit it and then so on. Whatever, this is also fine. Good. Any questions before we go to the Python implementation? Okay, so I'll wait for a moment. I'll show you the question. We'll be doing it next day with another sampling technique, which is called the upper confidence bound, but we'll not do it today. Slowly we'll start. So the Bandits algorithm in Python is something like this. Say we have 5 arms, and the 5 arms are given by uniform 1, 2, and so on. So I'll be showing it in the code. So 3 uniform distributions and 2 normal distributions. Okay, so the sample you sample from them. So I'll go back to today's presentation and just write it down. So you have the problem. The problem is, so you have to implement. So Bandits 1 is uniform 1, uniform 2, uniform 3, normal 1, and normal 2. So we have 5 distributions that the reward functions are sampled from. You are told to do a Bandits algorithm to choose the best strategy of choosing an arm. Okay, so this is the overall idea. So I'll keep this. I'll stop sharing from my tablet now. So if you don't have any question that I want to write, I'll go to my computer screen and show how it works. We'll keep this to the side and try to understand. Okay. Okay, I'll share my screen. Can you see my screen? Okay,
Yes.
great. So now, okay, let me just put this to the right and just open this over here. Okay, where is the algorithm that I wrote? Towards the lower half. Okay. This is the algorithm. I can't see you speaking now, so please, whenever you have a question, please stop me and ask the questions. Okay. Okay, rather I'll just keep join from my tablets and it will be easy, I think. Just give me a moment, then I can see you all as well. Oh, yeah, fine. So here I wrote a few functions. They're being so I imported simple packages in Python. Sampled this is the sampling reward function that the environment is giving you. If the distribution is uniform, so you sample from a uniform distribution based on the parameters. And if it is the normal distribution, you sample from the normal distribution based on the parameters. That's it, but there's no algorithm there, but yeah. So now I define the bandits class over here. The bandits class is something like this. So say the reward details are given to you. Say I have 5 arms for the bandits algorithm. You have a uniform 3 uniform distributions and 2 normal distributions as we discussed. Here we have the first one is normal 0, uniform 0, 1. Second one is uniform -1, 2. Third one is uniform 1, 2. Normal is 0, 1 and normal distribution 1.52. So first of all, seeing this reward function, what do you think should be the best strategy for the agent? Which will maximize its expected reward? Anyone? If you have followed my the distributions of uniforms and normals before just going into the algorithm, a fun exercise would be, what is the objective is to get maximum expected reward. Which has the maximum expected reward here? Which of the arms? So the first one here is the expected value is the first one, the expected value is 0.5, right? B minus A by 2. Second one is 1.5. This is the expected rewards. Expected values. The third one is, sorry, I didn't, did I write it correctly? No, it's 0.5 again. B plus A by 2, the midpoint of the two. And then this is 1.5 by 1.5. The second one, the normal distributions are given by the mu and sigma parameters. So it's 0 and 1.5 respectively. So which are the most beneficial actions? Anyone? Most beneficial actions would be actions are A3, like if this is 0, 1, 2, A2 and A4. Zero indexed. Okay. So let us see what we do. So as you said, I initialize the Q function at a particular time as NP of 0 of 5. I said initialize 5 zeros. NT as number of zeros again. I don't use this learning rate yet, but I can comment this out for the time being. Need this. Okay, so cell dot the will we also the epsilon that I have over here, the amount of time the epsilon is. So now if I for epsilon, what does this tell you? Tell me. Don't concentrate on C. C will be seen next time, but epsilon means for the epsilon greedy algorithm, what will happen? Anyone?
Greedy choosing will be done in epsilon probability.
Okay, so greedy action selection will be chosen with 90% times here in our case. This is 1 minus epsilon times, as we saw. See the left-hand side, we saw this over here. 1 minus epsilon times 90% of the actions will be this. Okay, so now that is not the function that we want. Neither is the UCB. Say you want to learn now. And we just concentrate on the epsilon greedy part. So the see, I wrote an so number of steps I want to use for the algorithm to learn is say 100,000 or 1 lakh. So AT is self dot take action epsilon greedy. So what does epsilon greedy do? Let's go to the epsilon greedy code. Give me a moment. Here is the epsilon greedy. So whenever you randomly sample from between random 0, 1, so random dot people who are all of you are from coding background, I guess. But np.random.rand samples uniformly between 0 and 1. So therefore, whenever it is less than the epsilon, which means that this is with probability, that is with probability epsilon, with p is equal to epsilon. So you take a random action. That's what I'm trying to do. np.random.choice. And this detailed enums is you choose any action, choose any action out of the 5. Or you just take the argmax of your self.t. You add the, so this is exactly the first line I'm doing in this case. You add nt to be 1 and you return the action 80. Fine. So your step now has the action 80. So now I tell you, you observe the reward from the environment. Where is the observe reward function? Here you go. Observe reward was sample reward. Let's give me one. Self.observe reward. Here it is. So self.sample reward gives you call the sample reward function here. And then you pass the distribution name and the parameters. So this just gives you the reward from the environment that I have defined over here. And then the reward is obtained. That is RT. Next, you do the Q learning update. See, QT of 80 is the QT of 80 minus 1, RT minus QT of 80. That's exactly what I wrote by self of NT80. Because I'm already adding 1 beforehand. So that's fine. So that's exactly the algorithm I wrote. I update the Q value function. And now I try to plot a few things. I try to plot number of times an action was selected. That I do. Where is the plot function? See, I plot a bar function. That number of times the action was selected. And I plot a function of expected reward. So what is the average expected reward that you will get? That expected reward is given by, what will be the expected reward given by? The average of all the reward that you'll be getting, right? So this is the average reward. So average reward also, I do the same sampling over here and get the average reward. So let's see how does the algorithm perform. Okay, bandits only have not run. Okay, so I've run it 1,000 times. Let us see how does the algorithm perform. Look at this. So what is happening is, see, action 2, which was uniform 1.5 over here. Where is it? Yeah. Action 2, uniform, the average value is 1.5, is being selected most number of times. And then action 4, because that was also average value is 1.5, and you see that the reward slowly goes up to 1.5. That's the average reward that the participant gets. This is called the learning curve of the Bandits algorithm. The x-axis is the number of steps. So any questions for everyone? Is the implementation clear? I have uploaded the code. You can play around with the parameters and see. Is it fine? Any questions? Questions?
Are there any different algorithms to do the same job? For example, in the random choosing part, we
Yeah.
can give more probability to the.
We'll see that. We'll see that tomorrow. Next class on
Okay.
Monday, we'll see that there's something called as the upper confidence bound that I have plotted over here. You can see that as well. That's a more scientific way of doing things where you see the upper confidence bound is so fast it converges. It doesn't choose any other actions. It just knows. It just choose, but it just knows very certainly that 2 is very good and converges faster. We'll see that how to do that next time. But yeah.
Okay.
Yeah, but that needs a little bit of maths, so I'm just avoiding it today. So we'll do it tomorrow. I mean on Monday. That is called upper confidence bound action selection method. Okay, but this algorithm is clear, right? Epsilon-greedy, and we are able to see that we obtained the optimal strategy. Yes or no? Right?
Yes.
Okay, so if everything is clear and you don't have any questions, if you I'll stop sharing from my computer. Yeah. So if you have any questions regarding anything, you can just go ahead and ask me. I'll probably write things down. I'll wait for a moment or two before I stop recording. Any questions related to what we learned today? Okay, so we learned what is environment, what is action, what is reward. We learned what is a value function. We've learned what is a reward function, the probability distributions, and we learned how to learn these value functions using something called as action value theorem, like the bandits algorithm, that is Monte Carlo sampling in a online fashion. And once we learned that, we wrote down the algorithm and saw the convergence of it. So that's what we did today. So if there are no more questions, I'll stop recording. Okay.